Hello and welcome to the lecture 6 of group theory. In this video lecture, we are going to see two results which involves. So first one is, so these are the two things which we are going to study. So suppose G is a group, what we are given, G is a group, and we are going to consider two subgroups, H and K. So H and K are subgroups of G. Right? So we are given a group and we are given two subgroups H and K. What we are interested in this two things here. One is HK, whether this is a subgroup of G or not, whether it is a subgroup of G or not. This is the first question. And second thing we are interested in is number of elements in HK. So we are interested in order of HK. Let us say in terms of number of elements in HK, H and K, in terms of number of elements in H and K. Right? So that is depending on it depends on the order of H and order of K. So these are the two questions which we are going to study in this video lecture. So before proceeding, let us consider what is HK. What is HK? How it is defined? It is the set. If we want to write, we can write like this: X belongs to G such that X equals to HK, where H is in H and K is in the group K. Right? Or we can just directly write like this. This is HK such that H in H and K in K. Okay, so this is HK, just like coset we have seen. So this is HK. And before addressing this question, let us consider an example. Let us consider two examples first. So keep in mind we are observing these two things. First is whether HK is a subgroup or not. Second is the number of elements in HK. This is what we are considering. So before that, let us consider some examples. And let us consider only one group, S3. So examples first. For that, let us consider S3. And S3 we know. What is S3? E, phi, psi, psi square, phi psi, and psi phi. This is the standard notation that we have seen earlier. And we also know the relation. What is phi square? Phi square is identity. We also know what is psi cube. Psi cube is identity. What we know is what is phi psi? Phi psi is nothing but psi square phi. And what we know, psi phi. Psi phi is nothing but phi psi square. So these are the relations we know. So we have considered G equals to S3. This is our group. And what is order of G? Order of G here it is 6. And now we consider H and K. So consider H to be the subgroup cyclic group generated by phi, and that we know what is it, E and phi. So phi, and then consider phi square. Phi square is identity, phi cube is again phi, and so on. So that you have only two elements, E and phi. And consider the subgroup K equals to E and phi psi. Phi psi is an element of order 2. If you want to check, we can check phi psi is an element of order 2. How do we check? We check like this. So phi psi into phi psi. So by associativity we have phi, and then we take this 2. So we have psi phi and psi. Now what is psi phi? Psi phi is nothing but phi psi square. So this is phi psi square and psi. Right? So now this is phi square, psi cube, which is identity, identity. Phi square is also identity, psi cube is also identity. So this is an element of order 2, just like phi. Phi square is identity. So you consider phi psi square also is nothing but it is identity. So here, what we observe is order of h is 2 and order of k is also 2. So H has 2 elements, K has 2 elements, and our group G is S3. It has 6 elements. Okay, so now let us consider what is HK. So what is HK? HK, the element of H are multiplied from the left. So E into E. So we have E, then E phi psi, E dot phi psi, then phi E, so phi dot E, and then phi psi. So this is HK, which is nothing but E. E phi psi is nothing but phi psi. Phi dot E is nothing but phi. And what about this? Phi square psi. Phi square psi. Phi square is identity. Psi. So this is psi. Okay. So order of HK is 4 in this case. Which, if you compare with this is nothing but order of H into order of K. So in this case, okay. So now let us observe what is KH. Okay, KH. KH also we can write like this. What is KH? KH, so elements of K are multiplied from the left. So that will be E dot E and then E dot phi. Then phi psi is multiplied. So phi psi dot E and then phi psi is multiplied with phi. So I'm going to write this above, not below, so that we can compare these two. Right? What is this? E dot E is E. Right? So this is E. What is this? This is phi. This is phi psi. And this one. So this is phi psi, which is nothing but phi psi is nothing but psi phi. Psi phi is nothing but phi psi square. So phi square psi square. Phi square psi square is what? Phi square is identity. So that is psi square. And what is order of KH? Order of KH is also 4 here. So 4 elements in HK, 4 elements in KH when there are two elements in H and K. So total 4 elements here we have, 4 distinct elements. And let me write this again clearly. Okay, so is HK equals to KH in this case? So let us see. You have identity, you have phi psi, you have phi, but these two are different. Which two are different? This two, they are not same. So here in this case HK is not KH. So in this case, first example we have observed. And yes, our first question, what was our first question? First, whether HK is a subgroup or not. So what about this? Can you say it's a subgroup? HK, identity is there, phi psi is there, phi square is there, phi square is identity. What about psi? If you take psi is there, then psi square also must be there. Psi into psi square. Psi square is not there, so it is not closed under the operation product. Also, the inverse of psi is nothing but psi square because psi cube is identity. So it's not closed under inverse also. So HK is not a subgroup of S3, G. So HK is not a subgroup of S3. So that also we remark here. So HK So let me remark with some other color so we can notice. HK is not a subgroup of S3. Why? The reason is, so not closed, and uh, existence of inverse also fails. So inverse of all elements doesn't exist. So that is one reason. Another reason is by Lagrange's theorem. So this is also an important reason. By Lagrange's theorem, order of HK equals to 4, and 4 does not divide 6. 4 does not divide 6, order of S3. This is 6. Lagrange's theorem we had seen. Order of subgroup divides order of group. So if HK is a subgroup, it must divide its order. Number of elements in HK must divide number of elements in S3, that is 6. 4 does not divide 6, therefore HK cannot be a subgroup. So there are two reasons here. One can directly see, otherwise using Lagrange's theorem also one can see. And one thing to observe is HK is not equals to KH, and here we observe that this is not a subgroup. So two things, HK is not equals to KH and HK is not a subgroup. The reason is Lagrange's theorem, or directly we can say. Second thing is what we wanted to observe is what is order of HK, whether it's subgroup or not. Subgroup होगा कि नहीं होगा पता नहीं, but what is, how many number of elements are there if H and K are finite? What is order of HK? So here H and K has 2 elements, and what we observe, HK has 4 elements, KH also has 4 elements. So order of H times order of K. Okay, so that is the one example here. And now let us consider second example. So in the second example also consider S3 only, the group. So here also the group we consider. Example number 2, G equals to S3, again E, phi, psi, psi square, phi psi, psi phi. The relation is E is phi square and E is also psi cube. And then phi psi is nothing but psi square phi, and psi phi is nothing but phi psi square. So these are the relation. H we consider this subgroup generated by phi as it is as in the previous example, so that is E phi. And K we consider the cyclic subgroup generated by psi. So we have psi, we have psi square, then psi cube. Psi cube is identity, and again, so this is yes, order of S3 again here is 6. Order of H, what we observe is 2. Order of K, what we observe is here is 3. Right, so order of H is 2, order of K is 3. H and K are subgroups of G of order 2 and 3. And now first question, HK, what is HK? So let us compute HK. So HK equals to elements of H are multiplied on the left. So we have E dot E, then E dot psi, right? Elements E dot psi square, then phi dot E, phi dot psi, and phi dot psi square, which is E psi psi square, then phi psi. And what is phi psi square? Phi psi square here. Phi psi square is nothing but psi phi. Okay, so what we observe here, HK has become 6 elements, so entire group S3. So HK is nothing but it has become S3. Let us see what is KH. So KH, let me write here below and then we'll write above so we can compare. So elements of K are now multiplied from the left. So this is E dot E, then psi dot E, psi phi, uh, yes, sorry, first E dot E, then we can consider first E dot phi. So now E is over, so now take psi. So psi dot E, psi dot phi, then take psi square dot E, psi square dot phi, right? And then let me write on the top. So this is E, phi, psi, psi phi, psi square phi. Psi square phi is nothing but phi psi. So this is phi psi. So as you can observe, this is also all the 6 elements. So here in this case, what we have is hk equals to kh. So this is important, and everything is S3. So what is order of hk? Order of hk here is 6, which is again, we can write order of h times order of k. Order of h is 2, order of k is 3. And hk equals to kh in this case, which is important. As you can see, we have all elements are there. E is there, then psi is there, psi square is there, phi is there, phi psi is also there, and psi phi is also there. So as you can see, all elements, it is S3. So we have in this case hk equals to kh. One thing which I want you to observe here, even though hk equals to kh, it does not mean that the elements commute. That is why I have considered this example to remove this confusion. So even if I take hk, so this is the case. So remark, this is not, this is for just understanding, not for writing. So remark is this: if I take hk, in hk, if I take an element like this, small h, small k in hk, h in h, k in k, and if hk equals to kh, then this element also belongs to kh. What does this mean? This means we cannot say, this means hk equals to some k dash h dash for some k dash in k and h dash in h. This is important. It does not mean that these two elements commute. That is why I have considered this example. So let me write. So it does not mean, what does not, it does not mean hk equals to kh. See, this is a difference. This is the difference. If hk equals to kh, it does not mean that hk equals to kh. So this is not true, right? So see, when we take the product hk, that is also S3, and when we take kh, that is also S3. They turn out to be same, but we know here, what we know? We know phi psi is not same as psi phi. So this is not true in general. So when we say hk equals to kh, and when we take an element in hk, that element is also now in kh, but that does not mean that we can commute that two elements. So hk equals to kh, we cannot write. What it means, hk belongs to kh, that means hk can be written as some k dash h dash for some other k dash in k and h dash in h. Is it clear? So in this case, hk equals to kh, and what we observe. So observe that in this case, hk equals to kh, and hk is, is it a subgroup? Yes, it is the whole group S3, so it is a subgroup. In fact, the whole group, so it is improper subgroup. So in this case, hk is a subgroup of S3. Right, so based on these two examples, we have got some condition. Hk is not equals to kh, it is not a subgroup. Hk equals to kh, here in this case here, Hk equals to a kh, and what we have got, Hk is a subgroup of S3. So what is the conclusion? Of course, you cannot draw just conclusion based on these two examples, but this is just for understanding. The result which we are going to see is Hk is a subgroup of G. Given H and K are two subgroups of G, the product Hk is a subgroup of G if and only if Hk equals to Kh. So I am writing that result. Sorry. Yeah, so this is the result which I state as lemma. And very simple proof. So let G be a group, H and K be two subgroups of G. And the lemma states this. Hk is a subgroup of G if and only if Hk equals to Kh. So very simple result. In the two examples we have observed, in the first example Hk is not equals to Kh, it is not a subgroup. In the second example Hk equals to Kh, in fact the whole group S3, and it is a subgroup. So let us prove this. Proof is very simple, but as I always say, what we should do is we should create the proof, not just understand the proof line by line and then just remember. So we just don't follow textbook proof. What we do is we create the proof, observe the things, and then write in our own uh, understanding. So let us first assume. First assume that Hk equals to Kh. Let us first assume that Hk equals to Kh. Anything you can start with. Hk is a subgroup also, because it is if and only if we have to do both sides, right? So I have first assumed that Hk equals to Kh, and what we have to prove? We have to prove that Hk is a subgroup of G. Right? We have to prove that Hk is a subgroup of G. So subgroup, we are going to use that equivalent condition. We can just show that Hk is closed under the operation of G, and Hk, every element of Hk has inverse in Hk. For that first claim, let us call it claim 1. Hk is closed. Closed means it is closed under the operation of, under the product of G. Product we write, or we write better, we write operation. Or if you don't write at all, it is understood. Just write Hk is closed under the operation of G. So for closed, what we do, we take two elements and then we show that the product means the binary operation also belongs to Hk. So let x and y belongs to Hk. So x and y belong to Hk. This means what? How does x look like? So that then we can say that x equals to, I call it h1 k1, and y equals to h2 k2 for some, right, where h1 belongs to h1, h2 and h, and these two elements k1, k2 belongs to k, right? So x belongs to hk, so it is of the form h1 k1, where h1 is in h, k1 is in k. Y belongs to hk, so it is of the form h2 k2, where h2 belongs to h and k2 belongs to k. Then what is xy? So then xy equals to h1 k1 and h2 k2. Right? So xy is of this form, and we want to show that xy belongs to hk. Xy, when it belongs to hk, if the elements of h is on the left hand side, element of k is on the right hand side, then belongs to hk. So we want h1 and h2 together, k1 and k2 together, but that is not going to happen because we don't know whether what we know is hk equals to kh. We don't know whether these two people commute or not. So what we do is first let us bring them together. So by associativity, so this is what we write. This is equals to h1 and k1 h2 k2. What we have used here is I can write the reason associativity of G. So now K1 H2, what we are given, what we have assumed is we have assumed that HK equals to KH, but that does not mean that elements of H and K commute. This is the best example, so that is why we had considered this example. Here HK equals to KH, all elements are same, all elements in these two sets are same, but that does not mean you take an element of H, you can take an element of K and they commute. No, you can take phi from H, psi from K. Phi psi is not same as psi phi, so they do not commute, but the sets are same. I know I am repeating it again and again, but just to remove your confusion. But what we know is this guy belongs to KH. So this I can write as this equals to H1. K1 H2 I can write as H3 K3 and K2. Why I can write H3 K3? The reason is K1 H2 belongs to KH. This is equals to HK. This is what we are given. And so K1 H2 equals to H3 K3, where H3 is in H and K3 is in K. Right? Because we know KH equals to HK. So K1 H2, this is an element of K, this is an element of H. So K1 H2 is an element of KH, but KH equals to HK. So K1 H2 is in HK. HK elements K, they are of the form an element of H times an element of K. So K1 H2 equals to H3 K3 for some H3 in H, K3 in K. This much we know. We cannot say K1 H2 equals to H2 K1, but at least we can say K1 H2 belongs to HK. So that can be written as one element of H, another element of K. Right? So this is how we express. So K1 H2 I can write as H. Now again by associativity, I can write this one as H1 H3 and K3 K2, and this belongs to HK. Why it belongs to HK? Of course, H1 is in H, H3 is in H, H is subgroup, so that belongs to, it's closed. So because H1 and H3 are in H, K3 and K2, so they are also there in K, and HK, H and K are subgroups. H and K are subgroups. This is given. They are not just sets. They are subgroups. So they are closed. So their product is also there in H. Their product K3, K2 is in K. And therefore, this is an element of H. This is an element of K. So it belongs to HK. So we are done. This is closed. We have taken X and Y, two elements in HK. X is of this form H1, K1. Y is of the form H2, K2. What we have got xy is of the form some different h1 h3 k3 k2. We don't know what are this, but this is an element of hk. So xy is in hk, given x in hk and y in hk, so hk is closed under the operation of g. So now next property, so claim 2. I hope this is clear. First one was very easy. Claim 2, every element in hk has an inverse in hk. So every element in HK has an inverse in HK. Right? So let us take one element. Let X belongs to HK. What we want to show? We want to show that X inverse also belongs to HK. So X belongs to HK. This means what? So then I can write X equals to, again like that, HK, where H is in H, and K is in K. Right? So I can write X equals to HK, where H in H and K in K. Now what is X inverse? X inverse, so then X inverse equals to HK inverse. But HK inverse, we know what is HK inverse. This is K inverse, H inverse. Right? AB inverse equals to B inverse A inverse. So this is K inverse H inverse, but this belongs to KH. Why? The reason is K belongs to K, H belongs to H, and H and K are subgroups. So K belongs to K. We have K belongs to K here. We have H belongs to H here. So, and because H and K are subgroups, K inverse belongs to K, H inverse belongs to H. So K inverse H inverse belongs to KH. But this is same as KH is same as HK. That is, we have assumed. We assume that this is our first assumption. We are assuming HK equals to KH, and we are proving HK is a subgroup. So HK equals to KH, and therefore X inverse belongs to HK. Simple. So thus X inverse belongs to HK. So this was not difficult at all, right? Even the other side is not difficult. So what we have got, every element in HK has inverse in HK. So HK, hence HK is a subgroup of G. Hence HK is a subgroup of G. Right? So now next is the converse part. So conversely, assume that now this time we assume that HK is a subgroup of G. So we assume that HK is a subgroup of G. And what we prove? We have to prove that this is not the way to write, but this is just I'm writing to explain. We should not write like this. So just very orthodox, not orthodox, unorthodox method. Okay, so we have to prove that HK equals to KH. How do we prove that two sets are equal? Yes, we show that one is subset of, we show that HK is subset of KH and KH is subset of HK. So first we show that, which is again very easy. First we show that KH is subset of HK. So if I take an element in KH, I have to show that it is in HK. What I know is HK is a subgroup. Subgroup, that means HK satisfies all this property: closure, identity, associativity, and inverse. We can use all these four properties. Now we are free to use that. What we have to show that HK equals to KH. So first thing what we are going to show is KH is a KH is subset of HK. So let me take X belongs to KH. So then X equals to KH for some K in K and H in H. Now here is what we do is rough work. Right? So this is the rough work we do. Rough work is, that is what I said. We create the proof and then we write. In the book they write something directly. They do not show the back calculation. For us it is important to understand the back calculation. So once we understand this, we can write the proof on our own. So what I have is X equals to KH. This belongs to KH. Now I wanted to show KH is subset of HK. That means I want to show this X in HK. But I have an element of KH. K on the left side, H on the right side. So if I want an element of H on the left side, element of K on the right side, what should I do? The thing is that I take the inverse. Is it clear? I want this is C. This is an element of KH. I want an element of HK. So what I do, I take X inverse. So let me write X inverse. What is X inverse? So that is KH inverse. KH inverse is nothing but H inverse K inverse. Now H was an element of H, K was an element of K. So H inverse is an element of H, K inverse is an element of K, and therefore this belongs to HK. Now what belongs to HK? X inverse belongs to HK. शुरू कहाँ से किया था? X belongs to HK. We started from X belongs to HK. We want to show that X belongs to KH. We want to show that X belongs to HK. What we got, X inverse belongs to HK. Inverse આવી ગયું. But આપણે તો X જોઈએ છે. So how do we get X from X inverse? Is it true? If X inverse belongs to HK, X also belongs to HK? Yes, it is true. What do we do? Because HK is a subgroup. This is the important thing. Because HK is a subgroup, what we do is take X inverse inverse. That also belongs to HK. This implies X belongs to HK, right? Because HK is subgroup. HK is subgroup, right? So this is the back calculation, and that is how we prove this. So now we write them like the book. So the proof will be given by the back calculation. So what we have got here, see, in rough work we have assumed H inverse K inverse is in HK. So X inverse is in HK, and then we take X inverse inverse, which is X in HK. So now the proof. This is the rough work, which is the back calculation, and then we write the proof in our own way. So we are showing that KH is subset of HK. So what we do, we take, let X belongs to KH, X equals to KH for some K in K, H in H. Then, so sorry, I should select this one. Okay. Then H inverse belongs to H and K inverse belongs to K. Reason is, since H and K are subgroups. Since H and K are subgroups, so if H is in H, H inverse is in H. If K is in K, K inverse also is in K. So now that means H inverse K inverse. So this implies H inverse K inverse belongs to HK, right? And now what we are doing, H inverse K inverse is actually X inverse. What we are taking, its inverse. So that means H inverse K inverse and inverse of this also is in HK. What is the reason we are giving here? The reason is HK is a subgroup. So since HK is a subgroup, see, it is very simple. I did not want to confuse you more. This is, I know it's a very bad way of explaining. I could have easily done this without confusing more and without showing what the rough work, this, our idea. But I do not want to do that. When I was not experienced enough, I used to explain like that, straightforward. That student may find it very easy to understand. Okay, so this is in this, this is in this, and so on. Very straightforward proof. But then this is a very bad way of understanding mathematics. This is what I believe. આમાં થોડું confusion કર્યું હશે create, but what I believe is when we are creating proof like this, rough work always helps. So this is how we are actually doing, and then like book we are writing કે આપણે અહીંયા શું જોઈએ છે. So we wanted H inverse here, K inverse here, but how do we get the idea? So that is why I do the rough work. I know by this method I have confused you a bit more, but this is the correct way to understand. I could have easily done that, and I used to do when I just joined as assistant professor in my first second year. I used to explain like this, line by line, everything easy for the student. But then in the exam they remember this. This is, I don't want to you to do this. I want you to understand this. Okay, so now we have, so this is nothing but what is H inverse K inverse inverse. So this is K inverse inverse, which is K, and H inverse inverse, which is H, which is nothing but X, and that belongs to HK. So we started with x in kh and we have got x in hk. So hence kh is subset of hk. So we have done first part. Let us call it 1. This is how we do by 1 and 2, hk equals to kh. So now the second one. So now we show that what remains to show, hk is subset of kh. So as usual, we start an element in hk. So let x belongs to hk. So then how can we write x? X is of the form an element of h and times an element of k. So where x equals to hk, where h is in h and k is in k. Right? So this is how x is. And again, rough work. Rough work always helps. I can give you direct proof, just a matter of 2 minutes, but that will not give you any idea. You will feel okay, this is very easy, but why you have to think like that, that is also important. એકાદ રિઝલ્ટ ઓછું થાય તો ચાલશે પણ મગજ કામ કરવું જોઈએ નહીંતર કંઈ ફાયદો નથી. Okay, so let us do our rough work as we have done in the previous case. So as usual, we start with x equals to hk. It is an element of hk and we want to show that x belongs to kh. We are showing this hk is subset of kh. So what we want to show, x belongs to kh. So kh માં કેવા elements આવે? K is an element of k is on left hand side, element of h is on right hand side. So from this hk we want to cook up some element of kh. What should we do? Take the inverse. That is the thing. So x inverse equals to, as we have done in the previous case. Let us see whether it works or not. I don't know. And this is what hk inverse. Hk inverse is k inverse h inverse. This belongs to kh. This certainly belongs to kh. Oh, but this is x inverse is in kh. What we wanted x in kh. What should we do? Can I take x equals to x inverse? Inverse belongs to kh. This is a big question. I know this element is in kh. What about this inverse? We don't know anything about it inverse. So why we don't know anything about inverse? Because we don't know whether kh is a subgroup or not. What we are given is hk is a subgroup. This is what we have assumed, right? Hk is a subgroup. And what we are proving? So here, now we have assumed that hk is a subgroup. We are proving hk equals to kh. So hk has, every element has inverse. But here there is something which is opposite. X inverse belongs to kh. So if I want x in kh, I should take again inverse, x inverse inverse. That will give me x. But there is no guarantee that x inverse ka inverse will belong to kh. When the element belongs to kh, that is fine, but its inverse belongs to kh. For that, kh has to be closed, has to be a subgroup, or at least every element of kh must have an inverse in kh. We don't know anything about that. So there is a problem. And that is why rough work helps. So what is the problem here? Do you realize there is some problem? Here we can come and we cannot take the inverse. Inverse is already allowed. So અહીંયા તો કેવું થવું જોઈએ? We should arrive यहाँ पे आने से पहले ही हमारे पास x होना चाहिए. Right? तो इसका मतलब कि we cannot take inverse later on. What we can do is we can take inverse previously because we won't know hk is a subgroup. So I am extending my rough work a bit. So this is again my extended rough work. આવું એક્ઝામ મને લાગતું નહીં તો પેપર તપાસવાળા હેરાન થઈ જશે. So this is my extended rough work. So what we do, we take x equals to hk in hk. So this is improvement in our rough. So inverse is, we know HK is subgroup, so inverse is allowed here. So what we take is X inverse belongs to HK. So let X inverse equals to HK no element, and so let it be H1 K1. But then this implies what is X? X is HK, X inverse is K inverse H inverse equals to H1 K1. And what we want HK. HK કરીએ તો પાછું શું કરીએ? Again take inverse. So K inverse H inverse equals to H1 K1 inverse. But this is what? HK equals to K1 inverse H1 inverse. Now this is an element of KH. So finally X equals to HK is an element of KH. I hope this is clear and it is not too much confusing. Let me write now. So how do we write? So X equals to HK for some H in H and K in K. Since HK is subgroup, what we are using, X inverse पहले ही HK में ही ले लेते हैं, उसके बाद जाते हैं. So since HK is a subgroup, X inverse belongs to HK. Then X inverse equals to, we can write H1 K1 for some H1 in H and K1 in K, right? But this means, that is, what is X inverse? X equals to HK. So that means HK ka inverse equals to H1 K1. See, હવે આપણે HK કેમાં જોઈએ છે? We want HK in KH. This HK we want in KH. So what we take again inverse. So this implies HK inverse, take its inverse. Clear? Equals to, what is this? H1 K1, taking inverse on both sides. So this implies take inverse. So I have got HK. What is this? This is nothing but X. And what is this? H1 K1 inverse, which is K1 inverse H1 inverse. This belongs to KH. Why? The reason is, since K1 K का element है, H1 H का element है, and K and H are subgroups. So K1 अगर K में है तो K1 inverse is in K, H1 inverse is in H, because H and K are subgroups, and therefore K1 inverse H1 inverse is in KH. So we started with something here. We started with X equals to HK. X is an element of HK. We have got X equals to HK is an element of KH. So what we have proved? So therefore we have proved HK is a subset of KH. अगर आप एग्ज़ाम में अगर ये याद रखते हो, भूल भी जाते हो, there is no problem. What you can do is do something like this, rough work, and then decide how do you want to write, and then you can write it here. Right? So almost this proof also is similar. I have written the same thing here, nothing new. But only thing is that if I start writing this, I realize okay, X inverse X inverse is an element of KH, but उसका inverse X KH में आएगा ज़रूरी नहीं है, because KH is not given to be a subgroup. What we are given, HK is a subgroup, so better start with HK inverse पहला जो वापरी लेवन, then use that inverse part initially itself, and then come to KH. Then you will automatically come to KH by creating such a new element X inverse in HK, and then taking the inverse on both sides. But if I give you this proof, you will understand it directly without showing this rough work, but then you will have to remember it during the exam. Now even if you forget this part, you can try out like this, and then you can realize कि कुछ problem है, then you will realize that X inverse has to be taken before, and that's how you come to the proof. So this is important actually, this back calculation. Right? This is important rather than this proof. Coming to the proof, creating the proof ourselves, thinking ourselves is more important than just understanding the proof and remembering it, writing in the exam, getting full marks. That does not make much sense. Okay, so now this is number 2, and yes, finally we want to write a sentence which makes us very happy. Hence, from 1 and 2, we have hk equals to kh. So hk is a subgroup if and only if hk equals to kh. Okay, so that takes care of our first purpose, hk. When hk is a subgroup, given h and k subgroups of G, hk is a subgroup if and only if hk equals to kh. Now coming to the second purpose, our second observation. So what was our second observation? What we are looking for is this. What is order of hk? Right? What is order of hk? That was our second purpose. I don't think I can now do that result in this video. Let me go back here. So this is order of hk in terms of elements of h and k. So let us, yes, what did we observe in the first two example? Order of hk equals to order of h times order of k. So that was our observation. So and that feels natural. That if we have something like this, h is a1, a2, a3, a4, right? So suppose four elements are here, and let us take k equals to b1, b2, b3. There are three elements. Then how many elements are there in hk? So hk, an element of h times an element of k. So of course a1 b1, a1 b2, a1 b3, and then similarly a2 b1, a2 b2, a2 b3, then a3 b1, a3 b2, a3 b3, then finally a4 b1, a4 b2, a4 b3. So this is the thing. So if order of h equals to h has four elements, order of k is it has three elements. Naturally, one would like to think this. Ketla was 12. There are 12 elements, 3, 3, 3, 3, and which is order of h times order of k. But let us now consider more example whether this is true or not. Right. So this is we are not sure. Let us take one more example. The reason is h and k are groups. If h and k are groups, when we multiply two elements, the same combination can be possible in some other way also. So let us take one more example, which was the purpose example number 3, before considering the proof or before even stating the result. So this is example number 3. Now we will consider additive group. So G equals to Z12. This we have seen very first lecture, Kadiyal Vadu joyu હતું ને Z12 with addition modulo 12. So this is nothing but 0, 1, 2, 3 and so on, 10, 11 and then 12 is again 0. So with plus 12, this is how we write. So this is what? Addition modulo 12. Right, so this is our group, and H is let us consider the cyclic group generated by 2. So identity 0 has to be there, 2 has to be there, and remember this is additive group, so not powers. Right? So 2 plus 2, 4, 2 plus 2 plus 2. It's not 2 cube, it is 2 plus 2 plus 2. So 3 times 2, not 2 raised to 3. It is 3 times 2, that is 6. Not 2 raised to 4. Additive group, so 2 plus 2 plus 2. So this is not 2 into 2 into 2. So this is 8, 10, and then 12. 12 is 0. So this is H. What is order of H? Order of H is 6 elements here. And K is, let us consider the cyclic group generated by 3. Cyclic subgroup generated by 3. So 0 is there, 3 is there, 3 plus 3, 6. 3 plus 3 plus 3, 9. And if we add 3 4 times, it gives us again 0, 12. So that is 0. So order of K. Order of k is 4 here. So if we have just like this, so if we have 4 elements here in H, 3 elements in K, what is expected, as we have seen in two previous examples in the beginning of this lecture? 12 is the expected number, but it is not going to be. Let us see in this what it happens. So here there are 6, here there are 4. Why it is not going to happen, you can clearly tell from this. HK is anyway subset of G. And H is a subgroup, K is a subgroup. So if I take an element of H, if I take an element of K, and if I take the product, so H and K are ultimately elements of G. So product also G is closed. So it has to be in G. Here G has 12 elements. So here it cannot be 6 into 4, 24. 6 plus 4 in either, 10 in either. So what is, let us observe what is HK. So HK, that means I have to, now this is additive, not, oh, so I should not write HK, what I should write is H plus K. Is it clear? H plus K is because additive group. So HK is not actually product. HK is H star, K star, which H belongs to H and K belongs to K. So here we have H plus K, where H belongs to H and small k belongs to capital K. So we have addition. So 0 plus 0. So we have 0. 0 plus 3 is 3. Then 0 plus 6 is 6. 0 plus 9 is 9. Then 2 plus 0. So that is 2. Then 2 with added with all elements of K. So H, an element of H plus an element of K. So let us fix 2 and then add with all these 4 elements. 2 plus 3 is 5. 2 plus 6. So 2 here, 6 here. So 2 plus 6, 8. And then 2 is fixed here, here 9. So 2 plus 9, 11. So this we have 4 elements. Now 4. 4 plus 0, 4 plus 3, 4 plus 6, 4 plus 9. So what is 4 plus 0? So that is 4. 4 plus 3, that is 7. 4 plus 6, 10. And 4 plus 9, that is 13. But modulo 12, so that is 1. Okay. So now 6. So 6 plus 0, that is 6. 6 plus 3, 9. 6 plus 6, 12. 12 is modulo 12, it is 0. And 6 plus 9. 6 plus 9, that is 15. 15 modulo 12, so that is 3. And now 8. 8 plus 0, so 8. 8 plus 3, that is 11. 8 plus 6, 14. 14, that is 2. And 8 plus 10, 8 plus 9. What is 8 plus 9? 17, so that is 5. Modulo 12 we are taking. And then finally 10. 10 plus 0, that is 10. 10 plus 3 is 13, that is 1. 10 plus 6, 16. 4. 10 plus 9, 19, that is 7. Actually we have 24 elements. There's 4 plus 4 plus 4 plus 4 plus 4 plus 4, 6 times. But all these elements are in the group. Group में 12 elements. There are not more than so. Let us see how many elements are there actually here. So 0 is there, 1 is there. We cannot repeat the elements in the set, we know. So 0 is there, 1 is there, 2 is there, 3, 4, and everything is there. You can observe this is all 12 elements. So this is nothing but Z12. So here order of H plus K equals to 12. This is not equals to order of H, order of K. H plus K or HK. This is same. અહીંયા plus ના આવે. Right? So here there is no plus. Plus here because it is an additive group, so it's just a notation. So it is not order of H times order of K. The reason you can see some repetitions are there, of course. Only 12 elements here, so there are repetitions. Otherwise, if you take any other example also, proper subgroups, there are going to be repetitions. But then if you take some Zn larger n, then our example will be so much lengthy. So 0 is here, 0 is here, which I strike off. Then what else? So 3 is here, anywhere else 3. So 3 is repeated again, so 2 times 3 is coming. And then what else? 6. So 6 is here once, 6 is here again, so I strike off. 6 is also coming twice. What about 9? 9, is there 9 anywhere? Yes, 9 is here also. So 9 is striked off. Then 2. Where is 2? Here. So 2 is also appearing twice. Then 5. Bar color નથી હોય મારી પાસે. 5 is also appearing twice. Then 8. What about 8? 8 is there. Yes, 8 is appearing twice. Every element is appearing twice. As you can see, 11. 11 is also appearing twice. And then I'm running out of colors. Ultimately, there will be a white color which will not appear. And this is yellow, at least you can see this yellow color. 4. 4 is also appearing twice here. And then I can use marker also, uh, highlighter. So then there is 7. 7 also appearing twice. And then there is 10. So there is 10 and 10 also appearing twice. And there is Bolambu Cyber 1. 1 is also appearing twice. So each number is appearing twice, as you can see here. So that actually we get 24, right? We should get 24, but each number in it is appearing twice. The reason, uh, how many elements are common here? Can you check? How many elements? Oh, this is marker. I don't want marker now. I want back to pen. Okay, so that is yellow color. How many elements are common here? What is H intersection K? H intersection K is identity. Of course, it is there. 2 is not there. 4 is not there. 6 is there. Two elements are there in H intersection K, and that is why every element is appearing twice. So what we expect, before going to what we expect, let us make an observation, one more observation. So here how many elements are there? Total 24, but we are dividing by 2 because every element is appearing twice. Actually, this was the case in the previous two examples also, but we did not notice. Why did we not notice? Because there was no element common in H and K. So let us go back to the previous two examples. So here let us, yes, take example 1. Okay, so I'm writing here what is H intersection K. So H intersection K here is no element, only one element common, of course. एक तो आवे, one element is always there, which is identity because they are subgroups. So one has to be there. So order of H intersection K is 1 here because only identity is common and these two elements are different. So this is nothing but upon order of H intersection K, which is 1 in the denominator. That is why we did not observe. Example number 2. Let us go to example number 2. Yes. What is H intersection K here? H intersection K, again, of course, identity will always be there. There is at least one element, no other element. Psi square here, there is phi here, so there is no other element. That means here also it is 1. So what we got is order of Hk equals to order of H times order of K. But we are dividing actually by 1 because here it is 1. But in the last example, third example, what we have seen recently, we have taken H intersection K is 2. And that is why the reason is every element is appearing twice. So what our result is, of course, you now have realized what is order of Hk. It is nothing but order of H times order of K upon order of H intersection K. Why it is happening? Let us see. So what we are seeing here is just a motivation. It is not a part of the proof. Still, I have not stated the result. So suppose H intersection K is identity. As in the previous two examples, we have seen that this is identity. Then we want to show that there are no repetitions. So all repetitions only come when H intersection K has elements. So suppose H intersection K is identity. And suppose there are repetitions. Suppose let us see what happens. Suppose there are repetitions of elements of HK, not HK, but we can write of the form HK. That means suppose suppose HK equals to H1 K1 for some H not equals to H1 in H, but H1 is not equals to H, and K1 in K but k1 is not equals to k. Right? So suppose they are two distinct. H1 is not H, K1 is not K, but still H1 K1, HK is same as H1 K1. Suppose one element can be written in two different combinations. For example, here, see 2 was appearing here. So 2 was nothing but 2 plus 0. So this is also 2, 2 plus 0. And 2 is appearing here also. So how did 2 appear here? 8 plus 6. So this is 8 plus 6. That is 14. That is also nothing but 2 mod 12. Right? 2 mod 12. So see, 2 is appearing twice. So suppose something like that happens here. Then what can we say? So if hk equals to h1k1, then multiply h1 inverse on left. So h1 inverse hk equals to, if I multiply h1 inverse on left, this is I get with k1, and now I multiply k inverse on the right. So h1 inverse h equals to k1 k inverse. Now observe that this is an element of h, and observe that this is an element of k, but both elements are equal. H1 inverse h, because they are all elements of h, so they belongs to h, their product belongs to k, but they are equal. So this means h1 inverse h belongs to h intersection k, and similarly k1 k inverse, k1 k inverse, it's an element of k, but k1 k inverse is also h1 inverse h, which is an element of h. So this is also an element of h intersection k. But what we have assumed h intersection k is we have assumed to be singleton identity. That means एक cut possibility है, the only possibility is h1 inverse h equals to identity, and here k1 k inverse equals to identity. But this gives us if I multiply by h1 on both sides, then h equals to h1, and k equals to, if I multiply by so k1 equals to k, if I multiply by k on the right side, both sides. But then this is a contradiction, because we have assumed like this here, that this, so here also there is a contradiction. This is not possible because h1 is not equals to h, k1 is not equal to k. That means I mean, if I assume this, then no repetitions are allowed. And if the repetitions are allowed, then h intersection k, either there is contradiction here that this cannot be singleton identity. So you see, repetitions are related with the order here. What is h intersection k? That many times repetitions will be there. So that leads us to the statement of the next theorem, which I'm not going to prove here now. It will be, of course, in the next video, as my idea was there. But I thought maybe I could do two results, but I've considered examples, so it is not possible now. But let us consider the statement here. Then we'll continue the proof in the next video. So next class we are going to discuss all this. If you have any difficulty here, so the idea is. So the theorem is statement is, let G be a group and H and K be subgroups of G. And this is very important result. Then order of HK. How many elements are there in HK? Of course, list तो बनाऊँ पड़े. बनाऊँ पड़े list में order of H times order of K, but then there will be repetitions. Order of H intersection K. So this is one of the most important result that comes handy in problem solving also. So I think we should stop here. Okay, the highlighter. Okay, so now I think we should stop here. Next video we'll see the proof of this is it. But you can go through the motivation in this three examples that we had considered. Since it was coming for the same topic, so I had given the statement here. But now the video will be too long. I think already it has crossed more than an hour, and so it will be too long, which I don't want to make it. And so let us take one more lecture to do this. Then the other two topics are next two sections are very easy. They are just revisions, normal subgroups and quotient groups. And then we have homomorphisms, isomorphism, first isomorphism theorem. So that is all revision of the BSc, so that we can go quickly. Okay, so I stop here. See the video before joining in the meet, and we are going to discuss the same thing in the meeting. Okay, see you.